Like for distance vector, we'll do it in two parts. First, we'll do a theory part that is a bit abstract and away from the practical details of how we do it in the lab. And then we'll see how congestion control is done in practice in the internet. So we start with a theory. So this picture is showing something. What do you see on this picture? Yes? Congestion. Anything else? You see a cyclist. It's in Paris. It's a picture I took in Paris from an intersection. And you see this cyclist. There's a cycle path here. And this guy is very bold. But none of the two things are the ones I would like to illustrate. There's something else in this picture. Something very specific of Paris, by the way. It's interblocking. You see that this car cannot move because this car is blocked, and this car cannot move because this car is blocked. So this car is blocking this one, which is blocking other car. So everybody's blocking everything. So this is not moving. They are caught in a deadlock. This is a symptom or a very frequent phenomenon, which is called congestion collapse. Congestion collapse means that the throughput of a system, here the analog of this in the internet would be a router or a link. When the throughput of a router of a link becomes zero because there's too much traffic, which is what is happening here. There's too much traffic, so things get blocked, which is paradoxical. When there's too much traffic, you would like the capacity to increase. But here the capacity decreases when there's too much traffic. That is called congestion collapse. So congestion means we have reached capacity. If this intersection can carry 10,000 vehicles per hour, if there's more than 10,000, it's impossible. You will not get more than 10,000 through it, so there will be queuing and delay somewhere. But congestion collapse is when the traffic is high and the capacity of the system becomes less. So here, at a congested period like this, the capacity is much, much less than 10,000 vehicles per hour. And that is exactly one of the root causes of why we need congestion control in the internet. Congestion collapse can happen also in the internet if we don't do congestion control. So that's the first thing we will learn, and then we will also need to discuss fairness and the different forms of congestion control. Let's start with a very simple example. Assume I have two nodes that are sending to two sources to two destinations over this small network that has 5 links of different capacities. The middle link is at 110 kilobit per second. This link is at 100, this one at 1000, this one at 100, and this one at 10. S1 is sending to D1, S2 is sending to D2. And S1 and S2 want to send as much as possible. And they don't use congestion control, which in practice we will see means they use UDP, for example. So S1 sends and wants to stream to D1. So the speed at which it will send, of course, is limited by the physical access. It cannot send at more than 100 kilobit per second. If it tries to send more, there would be a problem at the Ethernet adapter here. You would sense that the queue gets full or you cannot transmit, so the operating system will adapt. So it sends at 100 kilobit per second. This one sends at 1000 kilobit per second. Of course, at the first router, there will be a problem. There will be only a capacity of 110. So we have 10 more traffic in than the capacity out. So which means we are going to do something bad. What will happen? Well, we will queue here for some time, but after some time the buffer will get full and we will start dropping packets. To simplify the analysis, let me assume that dropping is perfectly fair and that we drop in proportion to the bit rate of each of the flows. So here we need to drop 90%. So I assume I drop 90% of the traffic coming on C1 and 90% of the traffic going here. That is assuming loss is proportional. That's a highly academic assumption. It's not true if we have small networks with few flows and you have FIFO buffers, because when you have FIFO, the queuing mechanics of FIFO is very, very complicated. You may have many non-intuitive results. Things like if you're unlucky, when your packet comes, you're always the last in a flow and the buffer is full, so your packet is always lost. And the guy that comes just after you, because your packet was lost, that has made some space in the buffer. In the meantime, the buffer has also been emptied a lot, so another flow might come. So there might be synchronization, and it's very hard to know in general. But if you have a large number of small flows in the network, this approximation will be true. Another case where the approximation will be true, that we will discuss in detail, is if you use ECN and things like RED. But as a first approximation, let's take this as granted. Now the question is, what will happen? At which rate will D1 receive data from S1? This rate is important because we know from our 101 information theory of 2 weeks ago that if the rate, which is the rate computed by the sending rate minus all the losses, that rate gives us the capacity. If we use TCP to code the packets, for example, from S1 to D1, this is the capacity in the sense of information theory. So, but now I'm simply asking how many packets per second will D1 receive from S1? And I'm proposing 3 possible solutions. Five more seconds. The correct answer is the most pessimistic, A, which is the majority. The ratio of accepted traffic at 1 is 10%. We drop 90%. So here we send 100 kilobit per second. At 1, 10 of this flow gets in, 100 of the other. Now at 2, what happens? Well, at 2, we have simply one flow that is going there. At 10, the capacity is 10. So as a first approximation, we drop nothing. Therefore, we get 10 kilobit per second here. So that was the correct answer. But it's interesting to look at the other flow. What is the other flow doing? Flow 2, that is sending at 1,000 kilobit per second, gets only 100 through here. And now, since the link is also at 10, sorry, it's at 100 here, is only at 10, it will get only 10 through here. So this one also will have a useful throughput of 10 kilobit per second. Now, if we compare what happens here, we have a network with 2 sources that want to send a lot, and at the end they both send at 10. But this is far from optimal. If somebody had given information to the sources, then it's possible for S1 to send at 100 and S2 still send at 10. The max that S2 can send to is 10. Anyhow, it cannot send more because of this link here. So it's ridiculous to have S1 be limited to 10. We should allow S1 to send at 100. If we do that, if we inform S1 somehow that it should send at 100 and S2 at 10, then there will be no losses, at least in this simplified network model, where if we reach 100% capacity, there's no loss, which is not exactly true, but very coarsely so. If S1 sends at 100 and this one at 10, then we have 110, 110, so that would work. So first take-home message, if Sources are greedy. Greedy means they send as much as they can, given what their local information is. If we do that, we have an inefficiency with no benefit to anyone. So a bit of regulation here in this network would make the thing same for S2 and better for S1. So we should do it. So greedy sources may be inefficient. Inefficiency is the first problem that is revealed here. Now we can understand a bit why the problem was occurring. The problem was that S2 sends too much. S2 has sent 1,000 kilobit per second of traffic, and this 1,000 kilobit per second of traffic is competing with the traffic from S1. But out of this 1,000, only 10 will make it through. So we have a system inefficiency. This guy is injected into the system 1,000 units of work per time unit. Out of those 1,000, we know that 990 will be lost. So it would be better if this guy injected only the 10. But this 990 units of work that are lost cause damage to others. They cause damage to S1 here. This is one of the symptoms of the syndromes and the root causes of inefficiency and congestion collapse. Yeah, it's analog to the road system. If we let all the cars go into an intersection, when we know it's physically impossible that they all go out, then they block the intersection and nobody can get out. If we had an access control mechanism to prevent them from entering the intersection upstream, then the intersection could work at a better rate here. So the same thing happens here, and you see we don't need a very complicated scenario. Of course, the numbers here are chosen for the thing to work, but you can easily imagine that such scenarios can occur. The 10 kilobit per second may be due to the capacity or the processing capacity of the server. So typically servers have different processing capacities for a given flow based on competition, for example. Perhaps both are YouTube servers, and although both are YouTube servers, but the capacity is the capacity at which the clients can process them, for example. Let's go one step beyond. Assume now a more complex network. This is a ring. Rings are very common in medium-sized networks. If you do a small network like a distribution network on campus, typically you do a star. In a star, of course, you have no redundancy. If you want a bit of redundancy, so in the backbone of a distribution network, you would typically do a ring because the ring is the simplest way to have some redundancy. If one link is broken, shortest path routing will find an alternate path through the longer side of the ring. Here I'm showing, for example, think of it as a metropolitan area, and this is the backbone of this area. And there are sources that send traffic to destinations that are not far away. To make the system easily tractable and possible to analyze with a closed form formula, I'm assuming a very symmetric thing that at every node there is one flow of information, one source that sends to a sink that is 2 hops away in this rotation sense on the ring. So there is source I that sends to destination I plus 2, and at every node there is one. So there are as many sources as there are nodes and edges on this ring here. Now what will happen if the source is sent at a very large rate, there might be congestion. If the rate of access here is much larger than the rate here, there might be congestion. So the rate lambda at which a source sends results in a rate lambda prime, which is the rate of information, the rates in packets per second or bits per second, at which the flow is sending here. The difference between the two are the losses at this link, similar to what we saw before. Now, the flow that it comes here, when it goes to this node, it's not shown here, but there is also, at this node, there is also a source. So if the rate of the source is very high, there might be again congestion. So lambda second is what is sent over the second link. And when we go out, we assume there is no competition. So what goes out is lambda second. So every source puts lambda into this ring. What the destination receives is lambda second. Of course, we can see that if lambda is very, very small compared to the capacity of the link, lambda prime is equal to lambda sec1 is equal to lambda, so the output rate is the input rate. But if it's very large, it will be less by the same phenomenon as we saw before. In fact, we can do a more detailed analysis. We can see that if C is the capacity of all the links and all links have same capacity, on every link there are two flows, the direct flow and the flow from the previous node, which is at its second hop. So if the capacity is larger than 2 lambda, then all flows can work on all links, there is no loss, and everything is fine. If this is not true, or more precisely, if C is strictly less than 2 lambda, there will be losses that we can compute. Now, if we look at the ratio of dropped packet, or the ratio of accepted packet at one link, we see that what comes in is lambda plus lambda prime. I'm assuming a completely symmetric scenario. So every source will have the same lambda prime, the same lambda second. So what is offered here on this link is lambda plus lambda prime. Lambda plus lambda prime is offered. The capacity is C. So the ratio of accepted traffic is C divided by lambda plus lambda prime. Just like before when we had 110 offered and 10 accepted, and we had 1,100 offered and 110 of capacity. The ratio of accepted was 10%. So here this is this 10%. This is the ratio of accepted traffic. Therefore, lambda prime is equal to the ratio applied to lambda. The ratio is here applied to lambda. This is lambda prime. Of course, it depends on lambda prime here. Similarly, for lambda second, we apply the same thing. Here we have another node that has the same ratio by symmetry. So lambda second is equal to this ratio applied to lambda prime. Now, the input variable is lambda. We want to analyze what happens when we vary the rate at which we load the network. And the output is lambda second, but we can compute here easily lambda prime. We see we have one equation with one unknown. C and lambda are known. We want to compute for lambda. This is an equation of which type? Can you solve this equation? I hope you can. It's an equation, a polynomial equation of degree 2. So we studied that at high school. We can solve for lambda prime as a function of the parameters, which are C and lambda. Then we can plug in lambda prime here. We can do that manually or ask Mathematica. At the end, we'll have a formula that will give lambda second from lambda. So I did it. And this is the formula we obtain. Lambda second is equal to this as a function of lambda. And here I'm plotting as a function of lambda the throughput, lambda second, per source. In a case here where the capacity is 20, for example. Then we see that as long as lambda is smaller than the critical value, which is half of the capacity, then everything that comes in goes out. So input is equal to output. That's the lambda second equal lambda line. And then after we get this, which is given by this formula. If we are curious, and so we see it decreases, that's the symptom of congestion collapse. That's our first thing here. Congestion collapse means for this network, if every source offers a lambda that's, for example, 100, then the throughput for everyone will be 3, right? You send at 100 kilobit per second, and the only thing that goes through is 3 kilobit per second. Whereas if everybody sent at 10 kilobit per second, everybody would get 10 kilobit per second out. So sending more forces everyone to get less. If we are curious and we want to see what happens when lambda gets very large, we can do limited development, an asymptotic expansion of this as a function of lambda when lambda goes to infinity, and we find that it is in 1 over lambda, which means when lambda goes to infinity, it goes to 0. So that is a very characteristic congestion collapse. If you increase the inputs into this network, eventually it gets completely blocked, nothing gets out. The throughput goes to 0. So take-home message. This is congestion collapse, like in the intersection in Paris, which is shown in another example here. So if we allow in a network sources to send at whatever rate they want, of course networks are more complicated than the 2 examples I've shown, but such cases have occurred in the middle of the 80s. There was an internet congestion collapse. At this time there was no congestion control. And in the mid-80s, there was one day where the throughput of the internet was a few kilobits per second. In the mid-80s, there were a few hundreds of nodes in the internet, so it wasn't a big thing anyhow. And the links between nodes were kilobits per second. But still, this congestion collapse occurred, and the mechanism for it is a combination of two things: the inefficiencies that we have seen in the previous example, and then a feedback loop. We see here that what happens is, because lambda is sending a lot of unnecessary traffic, it is killing the traffic of the next guy, but this is also killing the traffic of the next guy, etc., and then it comes back to me. So the fact that I send too much hurts me back here. So this feedback loop occurs when there are loops in the topology. This is why I picked here a ring topology. And of course, we need to do something in the internet. So if we let sources send as much as they can, which is a myopic view, it seems optimal because of information theory. I know if I send and I drop a lot, but I can still code to mask the drops. But no, this is not correct. If everybody does that, the system may collapse and everybody may get very, very little throughput. So next week, we will see what are the solutions to this embarrassing problem. Thank you very much. See you tomorrow.